Now in the case of UDP, there is a slight difference. The slight difference stems from the fact that TCP is actually using a connection oriented socket to deliver data, and UDP uses the connectionless. So actually, as an application level programmer, we are shielded from the gory details of what is going on as packets and everything. But just to sort of put that in better words, what we can say is the difference is that for a UDP server, once it has bound to a particular IP address and a port number on which it is listening for various clients, it just uses receive from and send to receive data from a client, and send to send data from a client. The client does the same. We'll talk about get host by name a little later. It is just basically taking input of the remote computer as a name, let's say yahoo.com, and will basically give out the IP address of that by doing a DNS query. But putting that aside, the subtle difference between a TCP and a UDP server is the fact that TCP uses the accept call to talk to a TCP client, and UDP typically uses a receive from call. When we go into a more programming example, things would be very clear. I'm sure some things might be a little hazy right now, but please wait, be a little patient. Once we go into the programming part of it, things would be very clear, can I assure you. So before we dive deeper, let's look at data structures. Now almost the whole of network programming just consists of these three data structures. Now when we said that we require a unique address for both the endpoints of communication to talk to each other, in the world of the internet, what that translates to is an IP address and a port number. So there has to be some way by which our program will tell the operating system that we want to bind to this particular port number of this IP address. Now in most cases, if the host is single homed, then there would be only one IP address. But assuming if there are many cards and many interfaces, there might be also multiple IP addresses on the same machine. Now to reduce the complexity in this example, we will just consider a single homed host, in which case there is just one IP address which is assigned to that computer, and we decide which port to listen on for the server process. For the client, of course, we just need the remote IP address of the server the client wants to connect to. In both of these cases, the way in which our application level programs is going to tell the operating system what is that address is accomplished by using these data structures. The first of which is sock ADDR. Now this contains an SA underscore family member and an SA underscore data. Now for all internet applications, SA underscore family is going to be PF underscore INET. We'll talk about some of these constants later. For the time being, you can just assume this. And this SA underscore data is where we are going to put in the IP address, port number, etc. of the server we want to connect to, or for that matter the port and IP we want to bind to. Now as you can see, it is very cumbersome to add all these things inside the SA underscore data. So make this much more simpler. Programmers have basically used the sock ADDR underscore in structure. Note that both these structures are of the same size. And actually when we will be programming, we will be using the ADDR underscore in structure and cast it into this structure while passing it as an argument. Don't get confused. Once we go into the programming, all these things will be crystal clear, and actually it is trivial. Actually hearing to this is more confusing than actually doing it as a programming exercise. To keep it simple, sock ADDR underscore sin once again contains the sin underscore family, which is same as the SA underscore family which we talked previously. Now the SA underscore data is broken up into three sub members, which is the sin underscore port, sin underscore ADDR, and sin underscore 0. The sin underscore port contains the port number, sin underscore ADDR contains the IP address, and sin underscore 0 is just a pad. Now to get some of the basics straight, actually sock ADDR can be used for a variety of other reasons, not just for internet or network communication. Sock ADDR underscore n on the contrary is a particular structure just used for internet communication. So that is why the slight difference between both of them. Also we notice that the IP address here is another structure called in underscore ADDR. Now this is nothing but a 4 byte long integer. which is what an IP address actually is. Now, before we dive deeper, there is one another small understanding which is required, and that is of byte ordering or EDNS. Now, EDNS is basically the attribute of a system which indicates whether integers are stored from left to right or from right to left. Let's quickly take an example to understand this concept. Let's say that you have a short int. A short int is 2 bytes long, and that is, let's say in this example, is 0xAABB. We are writing it in hex to be able to map that in memory much more easily. So now there are two ways to store this 2 bytes in memory. One is that in memory position 0 you store AA, and in memory position 1 you store BB. This method of storing integers is called big endian format. And another way could be that we decide to store BB first and then AA. As you can notice, the memory locations are 0 and 1, which increase from left to right, but the bytes in which, the way in which we are storing the bytes differs a little bit. So the way in which a computer is going to store bytes into memory is totally dependent upon whether it follows the big endian or the little endian format. Almost always this is just a function of the processor, the microprocessor which runs on the computer. To make this example a little bit more clearer, let's take a larger integer of 4 bytes, which is AA, BB, CC and DD. Note that AA is 1 byte, BB is 1 byte, and so on and so forth. As we can once again see in the big endian format, that is from left to right, we can store this integer as AA, BB, CC and DD. Memory locations increasing from 0 to 3. In the little endian format, we will store DD first, then CC, then BB, then AA. So the point is, there are two ways in which bytes can be stored on a host computer. Now imagine that there could be a little bit of confusion if one computer stores and transmits data in big endian format and the other in little endian format. When these communicate, there could be a lot of confusion as to which byte should be picked up as the MSB or which should be picked up as the LSB. So in order to not get into such a confusion, it has been decided that for network communication, all data would be sent in big endian format. In the world of networking, this is called network byte order. And the byte ordering on the host computer is called host byte order. Now this could be either big endian or little endian. But the point is, when we send out data on the network, we will have to send out in big endian format. Now for our example, all our programming exercises will be on a Linux computer which is running on a Pentium 4 microprocessor. Now P4 is actually a little endian format storing processor, in which case whenever we are going to be sending out any data, we would have to convert integers and some of these structures in which the byte ordering matters from little endian to big endian before we send it out. World of networking, we would say that we are converting host byte order to network byte order. This is all very confusing now, but as we go into a very simple programming exercise, things would be much more clearer.